class, but
okay. Good afternoon, everyone. All right, so I don't have to ask anything. Problem 5 from section 5.1. Okay, we can do that. Okay. All right, so first, let us remember definition. So V, the vector V, is an eigenvector for a matrix A if A times V is a certain scalar lambda times V. Okay, so that's the definition of the eigenvectors. It means when A acts on it, A will stretch it. And that's the picture that you always see whenever you hear eigenvector. That's the picture that you see. So AV is a scalar times V, okay? Then lambda is an eigenvalue. These are the definition. Eigenvalue if we can find a non-zero vector x, so if ax has a non-zero solution. Means a number lambda, like lambda 2, lambda 3, lambda 4, is an eigenvalue if we can find a vector such that A stretch this vector by the scalar lambda and a non-zero solution, and that's really important. Okay, so these are the definitions. The non-zero solution is called the eigenvector. Solution is called the eigenvector that correspond to lambda. Okay, so these are the two main definitions, and then I remind you how we find those later on when the problem comes up. So in problem number 5.1, number 5 in section 5.1, this is the question. We have a vector 5 minus 3, 1. So that's a vector. Let me call it V, for example. And we have a matrix A, which is equal to 3, 7, 9, 7, 9, minus 4, minus 5, minus 1, 1, and 2, 4, 4. Okay. And the question is V an eigenvector for A? Is V an eigenvector for A? Okay, what does this mean? It means when you take A times V, does A stretches V by a scalar or it doesn't? It means, is this property hold, yes or not? So to check that something is an eigenvector is actually not hard. But they're not asking you to find it. They're asking you only, is it? So to check whether if it is or not, we just take A, we multiply it by V, and we ask ourselves, are we stretching V or we're not? That's how we proceed. So that's exactly what we are going to do. I'm going to take the matrix A and multiply it by the vector V and see what happened when we do that. So this is my A, and this is my vector V. So that's a 4 minus 3, 1, a 3, 7, 9, minus 4, minus 5, 1, 2, 4, and 4. And now I just multiply them. So it's a matrix times a vector. So I'm going to use the row column definition. So I will have 3 times 4. 3 times 4 minus 21 plus 9. So that's going to give me a 0, right? Okay. And now, of course, it's not. We're done, basically. And then minus 16 plus 15 plus 1. I'm getting 0. And 2 times 4, 8 minus 12. So I'm going to get the 0. Okay. And now the question is, all give 0, absolute. Now the question is this an eigenvector? In other words, can I write this as a scalar times the vector v? Yes or no? Let's see what the question is. Can I write this as a scalar times the vector v? Any answers? Yeah, the scalar could be 0. No question about it. This could be written 0 times v. So it means that v is an eigenvector because it's a scalar times v. It's a non-zero. V is not 0. It's the eigenvector, which is 0. So v is an eigenvector. So the answer, of course, it's yes. V is an eigenvector. And the eigenvalue that corresponds to it is lambda equal to 0. Is lambda equal to 0. In other words, the eigenvalue can be 0. It's the eigenvector, which is not 0. So here, this is an eigenvector, absolutely. And the eigenvalue that corresponds to it is lambda equal to 0. So that's the answer. Okay. Any other questions from the homework? Okay. So today, number 11, Chris. Okay. We look at number 11. So any vector would work. I don't quite follow the question. What do you mean any vector would work? Not any vector is going to give me 0, 0, 0. It's this vector that gave me 0, 0, 0. If I switch the vector, I'm not going to get 0, 0. Okay? All right. So let me look at number 11. And we have a matrix A, which is the following. 4 minus 3 and minus 2, 9. And the question is, find, I told you on the homework, drop the word basis. I'm going to define that today. And I told you only find the eigenvectors. And the question is, find the eigenvector that corresponds to the eigenvalue lambda equal to 10. Okay, so I told you, don't worry about the word basis. I will explain it today. Actually, that's what we're going to do today. But the question is, find the eigenvectors. So I'm giving you the, so find the eigenvectors that correspond to lambda equal to 10. Okay, so let us see. Yeah, I'm doing that. Yeah. That's number 11, right? Yeah, that's number 11, 5.1. Yeah, okay. So find the eigenvector correspond to lambda equal to 10. Now, how do we find the eigenvectors? To find the eigenvectors, we solve. How to find the eigenvector? We solve the system A minus lambda ix equal to 0. Sorry. So to find the eigenvectors, we solve the system A minus lambda I equal to 0. And this is intuitively, not intuitively, that's basically equivalent to solve AX equal lambda x. Okay, because finding the eigenvectors, it means I'm finding all the vector x such that A stretches by a factor of lambda. So finding the vector x such that A stretches by a lambda is actually equivalent to solve this homogeneous system, which is easier to solve. So now here we need to solve in our case, because lambda equal to 10, it means we have to solve A minus 10 times the identity x equal to 0. Okay, so that's how we find the eigenvectors. So let's do that. So we have first to compute A minus 10 times the identity. That's a 4, that's minus 3, minus 2, and 9. Minus 10 times the identity, 1, 0, 0, 1. So it's going to be equal to 4 minus 10, minus 6, minus 2, minus 3. We always take from terms along the diagonal. 9 minus 10, which is A minus 1. Okay, now we need to solve. So we set the homogeneous system and we solve. It's equal to minus 6, minus 2, minus 3, minus 1, and 0, 0. Okay, so I have to solve this system. If I am doing it, I have 6 and 2. I make it easy for myself. So I divide by minus 3, which is going to give me, sorry, by minus 2 I meant. That's going to give me a 3, and this is going to give me a 1. You don't have to, but this makes things easy for us. Minus 3 and minus 1. Now we have to row reduce. Always we row reduce. And we have to have an independent, a free variable. Otherwise, something is wrong. Give me 0 and 0. Now we solve. X2 is free. And the first equation read 3x1 plus x2 equal to 0. It means x1 is minus a third x2. And we write the solution in vector, parametric vector form. So if I set x2 equal to t, so we set x2 equal to t, so that's, okay, I'll write it right here. Set x2 equal to t, then this gives me that x is a scalar t times a third and 1, which means that the eigenvectors are all vectors of the form. So the eigenvectors are all vectors of the form scalar t times 1/3 1, where t is different from 0.
Because isn't it negative 1/3?
Did I do a mistake?
Yeah, I think it's negative.
Yeah, thank you very much. All right, minus a third down where t is different from 0. Okay, those are the eigenvectors. And t is different from 0 because eigenvectors are non-zero vectors. That's what the definition of eigenvectors. All right, so these are my eigenvectors. Now, how do we check? I check just to remind you that what those eigenvectors represent. Those eigenvectors are vectors. When I take A, I multiply it by them. The effect is to stretch those vectors by a factor of 10. So if you want to check, are you getting the right vectors? You take A and you multiply it by those vectors. So a typical vector here is a scalar times that. Now t is a scalar, I can move it out because multiplication, if you have A times a scalar times a vector, we can always take the scalar out. So that's property of the linearity of multiplying by a matrix. So this is A times minus a third one. I'm just checking, and I'm to make sure I'm doing it correctly. So this is equal to t times, and my A is 4 minus 2 minus 3, 9 times minus a third and 1. So it's equal to t times. Okay, now I do the math and see if I'm actually stretching by a factor of 10, yes or no. So here I'll have minus 4/3 from here, minus 2, which is going to give me minus 4 minus 6. So that's going to give me minus 10/3 here. And down here I have minus minus, which is plus. So I will have a 1 and I have a 10 in here. Okay, I'm just multiplying. And now, of course, I factor out my 10. I get t times minus a third and 1. That's my original vector. When A act on it, it's actually stretching it by a factor of 10. So what we did is correct. And if I had put 1/3 instead of minus a third, I would have seen the mistake immediately. Okay. All right, so this is for your questions. Now, I'm going to stick to the same example and talk about those eigenvectors a little bit. So the eigenvectors, there are a lot of them. So as every time I change t, I create a new one. So minus a third one is one eigenvector. Okay, t is not equal to 0 because by definition, eigenvectors are all non-zero vectors that has the property ax equal lambda x. Okay, that's the definition of an eigenvector. Okay, so where am I? Okay, I'm right here. So the eigenvectors, as we said, that all vectors of this form. So as t changes, I'm going to create a lot of them, infinitely many of them. And that's the picture. So the picture is like this. So how many eigenvectors we are? So this is minus a third in my problem, and this is a 1. So this is the eigenvector that correspond to t equal to 1. But then as I stretch it, I have another one. Stretch it, I have another one. I have lots of them. And I have both of them in the other direction. If I take t equal minus 1, so only the 0 vector is not in here. So I have infinitely many eigenvectors. We're going to give them a name. And we're going to call this eigenspace. And we're going to give it the notation E. The letters stand for eigenspace. And down here, I'm going to write 10, which is going to represent the eigenspace that correspond to lambda equal to 10. So all those vectors, we have infinitely many vectors. What characterizes them in this particular problem, they are all on this line. Okay, we're going to give them a name, and we're going to call them the eigenspace that correspond to lambda equal to 10. And now I define eigenspace in a more formal way. So this is the definition of the eigenspace. 1 minute. Okay. So eigenspace, I read it very, very slowly. So let A be a matrix and by n matrix. And let lambda be an eigenvalue for A, which is lambda was 10 a minute ago. Then the eigenspace of A corresponding to lambda that we denoted by E, the letter E stands for eigenspace. Lambda is the eigenvalue, is defined as follows. Okay, that's how we're going to define it. E lambda is the set of all the eigenvectors that correspond to lambda, but we're going to tag to it the 0 vector because 0 vector is not an eigenvector. So E lambda is all the eigenvectors that correspond to lambda with the 0 vector added. So in my previous picture, my eigenspace was basically the following. In the previous picture, we had that was minus a third, and that's 1. So I'm including 0 for the eigenspace. So the eigenspace is basically all the vectors which are on this line. This is really what the eigenspace is. together with the 0 vector. So I can say all the vectors which are on the line. So that's what the eigenspace is. Now we're going to define it a little bit more. What are the eigenvectors? So the eigenspace is basically all the solution, because how did we find the eigenvectors? To find the eigenvectors, we actually solved the system A minus lambda ix equal to 0. So the eigenspace is all the solution of the homogeneous system. Homogeneous, it means the right-hand side is the 0 of the homogeneous system A minus lambda ix equal to 0. Okay, so that's the eigenspace. Now, the solution of the homogeneous system, we gave it a name before. And what we actually call it is the null space. So the eigenspace is actually the null space. The null space of which matrix? Is the null space of the matrix A minus lambda I. Because A minus lambda I, that's the system I am solving. So the eigenspace basically is all the eigenvectors with the 0 vector added to it. But what are the eigenvectors? The eigenvectors are all the solution of this homogeneous system. And those were given a name, and we call them the null of A minus AI. That's really what we have. Now, when I defined the null, in my previous example, the example that I did a minute ago, let me use it to explain an idea. So in my previous example, when my matrix A, so the guys I did a minute ago, so when my matrix A was equal to the following, I'm going to take my matrix A. My matrix A was the number 10, 4, minus 3, and minus 2, 9. And lambda equal to 10 was my eigenvalue. In this example, what's E10? E10 is nothing more than the null of A minus 10i. That's really what it is, because E10 are all the solution of the system. So it means in my previous problem, all vector x, such that x is a certain scalar times the vector minus a third 1. That means E10 is nothing more than all scalar multiple of the vector minus third 1. But mathematically, linear algebra tell me, gave those a name. And we call this the span of the vector minus third 1. Okay, so that's really what E10 is, nothing more than the span, because every possible scalar multiple of this vector. Now, what's the basis? When we talked about the null, we introduced the idea of a basis. So now, so what's the basis for E10? It's a null space. So what's the basis of it? It means what are the vectors? When you span them, you get all of the eigenvectors, or you get all of the n, and they are linearly independent. In this particular example, the basis for E10 will be the vector minus third 1. That will be the basis for E10, which is really telling me that the eigenspace, it means all the eigenvectors that correspond to equal to 10 are nothing more than scalar multiple of these vectors. So this is the basis of E10 is actually this vector, or this vector. Let me see, minus 1, 3. Is this correct? Can I use this as a basis or this as a basis? Will it be the same thing? Absolutely the same, because what did I go from here to here? I just multiplied by 3. So both of them, minus a third 1 is this vector, and minus 1, 3, I just multiplied this by 3. So it's that vector right here, 3 times. So whether I take all scalar multiple of minus 1/3 1 or a scalar multiple of minus 1, 3, I'm going to absolutely get every vector on this line. So you can either use this or use as a basis vector. Now the dimension, let us remember what the dimension is. The dimension of E10 The dimension is the number of vectors in the basis. And the dimension here is equal to 1. Okay, so that's the idea of the eigenspace. So now I'm going to do one more problem where I actually rephrase the questions using the idea of a basis for the eigenspace. So I'm going to do one more problem with eigenvectors and eigenvalue, and probably this will be kind of summarize all the ideas. So I'm going to take the following matrix, and this time I'm going to take a 3 by 3 matrix, not only a 2 by 2 matrix, and we're going to work with it. So let A be the following matrix. So example, let A be the following matrix. -1, 4, 0, 1, 2, 0, 1, 4, -2. Okay, I'm going to do the whole problem now. Question number 1 is find the eigenvalues of A. Eigenvalues of A means we want to look for the scalars for which we can have vectors that are stretched by the scalars. Find the eigenvalues. Now let's remember, how do we find the eigenvalues? To find the eigenvalues, we do the following. We set the determinant of A minus lambda I equal to 0, and we solve for lambda. Okay, so let's do that. Sorry. Let's compute the determinant of A minus lambda I. First, I need to compute A minus lambda I. What's A minus lambda I equal to? So it's A. We're taking away from it lambda times the identity, which is a 1, a 0, a 0, 0, 1, 0, 0, 0, 1, -1, 1, 4, 2, 4, 0, 0, -2. And by now we should be able to know exactly what you get. Basically, you take lambda away from the term along the diagonal, and the other one are not touched. So you take lambda from the term along the diagonal, and those remain the same because you're taking 0 away from them. 0, 0, -2, minus lambda. So that's A minus lambda. Now I need to set the determinant equal to 0. So let's compute the determinant. Okay, so the determinant is -1 minus lambda, 1, 1, 4, 2 minus lambda, 4, 0, 0, -2 minus lambda. That's my determinant. Now let us compute this. Now, of course, we learned determinant, so we can do those problems. And if I want to compute the determinant, definitely we will do cofactor. We use the third row, and we're going to do cofactor expansion, so cofactor across the third row. Because there are a lot of zeros, okay, because we have a lot of zeros. So if we do that, we get equal to. Let us remember the sign, plus, minus, plus, minus, plus. So we're going to get -2 minus lambda, because the first two terms are 0, that's why we picked it, times the determinant of -1 minus lambda, 4, 1, 2 minus lambda. Usually finding eigenvalues is not an easy problem, because as you realize, for 2 by 2 we can do it. For 3 by 3 we already have to solve a complicated equation. So this is equal to -2 minus lambda times, okay, we multiply those by each other, and if you guys do it, you should be able to do it, you get that. Okay, just multiply, and you get that much. So we're going to set this equal to 0 and solve. Okay, to set it equal to 0, this could be factored. Actually, I can take the minus out here. I will have 2 plus lambda. And this one will give me lambda 2 and lambda 3. And that should be a minus, and that should be a plus. Okay, so you compute, remember, you have to solve the determinant equal to 0. So factoring is the best way to do it. Try to factor because that's easy. So it's going to give me what for eigenvalues? 2 plus lambda is 0, means lambda, and this is 0, so I will get lambda equal minus 2 from the first one, and this is going to give me lambda equal to 3. So I have two eigenvalues. So let's remember, to find the eigenvalues, you have to set the determinant of a minus lambda equal to 0 and solve for lambda. And remember, you're solving equal to 0, so you'd like to factor out the determinant because that makes solving easy. So always try to factor it out unless you can't, which is you use quadratic or whatever, but usually try to factor it out. Now we found those. Now question number 2 is, for each one of those eigenvalues, we're going to find a basis for the eigenspace that correspond to it. Okay, and this time I'm starting to use the word basis for the eigenspace. So question number 1 is, find the basis. Find a basis for the eigenspace that correspond to, I'll pick one of them, lambda equal minus 2. In other words, for eigenspace, or the notation is E minus 2. Okay, so that's my question. Okay, find the base for the eigenspace. It means basically I have to find all those eigenvectors. So we have to solve. So to do that, we need to solve the system A minus lambda I x equal to 0. So we have to solve this homogeneous system, okay, and which is a null space, and then we're going to find the basis for this null. That's what it is about. All right, so let's do that. Let's do that. What's A minus lambda I? So A minus lambda I x equal to 0. It means now there is a minus 2, so we have to be careful here. It means y minus 2i x equal to 0. That's what we have to solve, okay? Now we can make our life easier, and I say minus, this is like that. And because lambda is negative, so we have to be very careful. So let us compute a plus 2i equal to. So we take the matrix A, and we add to it twice the identity. And my matrix A. 1, 4, minus 2. Okay, and we add them, and then we solve. So if we add them, I will get minus 1 plus 2, which gives me a 1. The terms of the diagonal, we're adding 0 to them, they don't change. It's only those along the diagonal they change. I will have 2 plus 2, which is going to give me a 4 in here. And of the diagonal, they don't change. And finally, I will have 0. They don't change. And I have minus 2 plus 2, which is going to give me a 0. So now we need to solve the system. A plus 2i, 0. This is the homogeneous system I need to solve. So this is equal to a 1, a 1, a 1, 0, 4, 4, 4, 0, 0, 0, 0, and a 0. Now we're solving. We are absolutely solving the way we've always solved a system. So I have to go to the echelon form. I have a 1 in here. I have to make everything under it is 0. So I have to multiply this row by minus 4. So I will multiply it, and I'm going to get the following. It's a 1, 1, 1, 0. Minus 4 plus 4, it's a 0. Minus 4 plus 4, it's a 0. Minus 4 plus 4, it's a 0. This remain 0, 0, and 0. Okay, now we're solving. So here we have two free variables, x2 and x3 are free. So x2 is free. x3 is free. And x1, I have to solve it. Give me minus x2 minus x3. Now we have to write the solution in parametric vector form. So I'm going to put this to be my s. This is my t. And this will become minus s minus t. So if x is an eigenvector, x could be written as minus s minus t, s and t, which is equal to, we have to write in parametric vector form as we did for the null, because I want to get the basis. So it's going to give me s times minus 1, 1, 0 plus t times minus 1, 0, 1. Okay. So what is my eigenspace now? My eigenspace E minus 2 is all the eigenvectors with the 0 vector thrown into it. So my eigenspace is every vector of the form, a scalar times that plus a scalar times this. So my eigenspace now is nothing more than the span of those two vectors, because it's every linear combination of those vectors. That's my eigenspace. So let me make a comment. What we're doing, we're basically trying to find all the vector x that has the property. If I take a times x, I get minus 2 times x. That's really what we are finding, all those. But we said that this is really boiling down to solve this system. So now, what this solution represents, all those vectors that when you take a times them, you get minus 2 this vector, all the vectors that a stretch by a factor of minus 2. And we realize that every vector that has this property is a linear combination of this vector and that vector. So my eigenspace is nothing more than every vector of this form. It means every linear combination of those. It means it's the span of minus 1, 1, 0, and minus 1, 0, 1. And those two vectors are linearly independent because there is no way, there are only 2 of them, not 3. So we can spot them. They are not scalar multiple of each other. So note that those vectors are linearly independent. So a basis for E minus 2 will coincide with those two vectors. So a basis for E minus 2 for my eigenspace. So a basis for the eigenspace is actually those two vectors, minus 1, 1, 0, and minus 1, 0, 1. So this tells me that every eigenvectors that correspond to lambda equal minus 2 is actually linear combination of those two. Yeah, we will do that. We will do that. But first I wanted to do this one. Okay, the other one is not hard. And the dimension of E minus 2 is nothing more than the number of vectors in here, which is equal to 2. Okay. And geometrically, if you want, what this is telling me that E minus 2 is nothing more than the span of those two vectors. Those two vectors, when you span them, now I'm not going to draw them. Suppose this is minus 1, 1, 0. And forget about being clear. And this is minus 1, 0, 1. Means if I take the plane that's formed by those two vectors, the plane that's formed by those two vectors, that's E minus 2. And this is telling me if I take any vector within this plane, any vector, and any vector v in this plane, and I multiply it by v, I should get minus 2v. Any vector in this plane have this property because E minus 2 is the span of those two vectors. Okay. Now we have two eigenvalues. And I know that, and one of your classmates, what about the other one? The other one, we can do the same. So probably question number 2 I can ask, or now part C, find a basis for the eigenspace that correspond to the other eigenvalue. And my other eigenvalue was, if I take it back, my other eigenvalue was lambda equal to 3. And now it's the same thing all over again, but we have to solve a different system. So now we have to solve a minus 3 times ix equal to 0, okay, to find those. So we can do that. I will give you only the, so we're gonna set up here a minus 3i, 0, and we solve that. Now we can compute a minus 3i, that's my a, minus 3i, because I'm by 3, it means I take 1 along the diagonal, so this is gonna give me basically a minus 4 in here, and the 1 and the 1 would remain. And then for the second row, the 4 would remain. 2 minus 3 give me minus 1. The 4 remain. I have a 0. And the last row was a bunch of 0 and 0. And the minus 2, I have to take the minus 3 away from it, which is going to give me the minus 5. Okay. Be very careful. We should get a free variable. If I don't get a free variable, I did something wrong, because the determinant of this matrix is equal to 0. I have to have a free variable right here. Since the determinant is 0, it means the matrix is not invertible. I have to have a non-zero solution. So you guys do the math, I don't. And then if we do it correctly, I will get here. Actually add them. Minus 4 plus 4, 0. 1 minus 1, it's 0. 1, do I have a mistake somewhere? And 1 and 4 is 5. So that's 0, 0, 5, 0, 0, minus 5. That's a leading, and that's a leading. But this is not in echelon form, so I will have to go one more step to get to the echelon form. 0, 0, 1, 0, 0, 0, 0, 0. I skipped a step, so I added them, then I divided by 5. And now it's just a matter of solving. Leading, leading. This is my free variable. And this is going to give me the following. Let's read it very carefully. x2 will be my free variable. The last row, read x3, 0. And the first one is going to give me minus 4x1 plus x2 plus equal to 0. So if I solve for that, I will get x equal t times 1, 0, and this will going to give me 1/4. So in this case, my E3 is going to be the span of this vector. So every linear combination, every scalar multiple of it, because it's all of them. That's going to be my E3, and the basis for it is only one vector. It's going to be the vector 1, 4, 1, 0, or the simpler vector 1, but that's easier, 4, 0. Either one will be accepted as a basis. Okay. Now I need a little bit of terminology, more terminology, because we have to. So some terminology. Give me 1 second. So now we define the eigenspace. Now a little bit of terminology. Section 5.1 and 5.2 are actually really the same sections, the same idea. So terminology. let A be a n by n matrix. Then the determinant of A minus lambda I by itself, the determinant, when you compute it, it has a name. And we call it the characteristic polynomial of A. Okay, so if you have an n by n matrix and you compute the determinant, you get a polynomial. Polynomial, it means you get something like lambda square minus 2 lambda plus 1, or lambda cube plus 2 lambda square. It means there is no square root of lambda involved. That's what we mean by polynomial. And this has a specific name. It's called the characteristic polynomial of A. And it's a polynomial. The degree of the polynomial is the size of the matrix. So if you have an n by n matrix, the highest degree, when we compute the determinant, the highest degree of lambda is going to be the size of the matrix. And actually, we realized a minute ago when I gave you a 3 by 3 matrix, when we did the 3 by 3 matrix, and we computed the determinant right there, when I took the 3 by 3 matrix and I compute the determinant, the degree is 3 because I will have lambda, 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 which equal lambda to the power 3. Now, the equation, when we solve for the eigenvalue, means the equation A minus lambda I equal to 0, that we need to solve the eigenvalue is called the characteristic equation of A. So it's a bunch of terminology that we have to know. We call this the characteristic equation. So the determinant by itself is called the characteristic polynomial. The equation will call the characteristic equation of the matrix A. Now a little bit more terminology. Suppose lambda 0 is an eigenvalue of the matrix A. What does it mean? It's an eigenvalue. Eigenvalue means it's a solution of the characteristic equation. It means it's the solution of A minus lambda I equal to 0, because that's what the eigenvalue is. Then the algebraic multiplicity. The algebraic multiplicity of lambda 0 is the number of times the factor lambda minus lambda 0 occur when the determinant is completely factored over the real and the complex number. What am I talking about? In the previous problem that we did, it means this problem that I did a minute ago. That's matrix A. And I computed the determinant. As you realized, we got the factor 2 plus lambda twice, 2 plus lambda square. And lambda minus 3, this occurred only once. We say that lambda equal minus 2, we call that this has algebraic multiplicity 2, because the factor 2 plus lambda occurred twice when we totally factored out the determinant. Lambda equal to 3 is called algebraic multiplicity of 1. So if, let us say, you have a 4 by 4 matrix A, and you evaluated the determinant, and you factored it out. You factored it out till you can't factor anymore. And you got something like lambda plus 1 to the power 3 times lambda minus 4. Then lambda equal minus 1 is called of algebraic multiplicity 3. Lambda equal 4 is called algebraic multiplicity 1. So the algebraic multiplicity is the number of times the factor lambda minus lambda 0 is occur when the determinant is completely factored, not partially factored, when we totally factor it over the real and complex. Now the last definition is, suppose lambda 0 is an eigenvalue. Okay, then we have non-zero eigenvectors. Then the geometric multiplicity of lambda 0 is the dimension of E lambda 0. Dimension is the number of vectors in the basis of E lambda 0. So let me take you back to the previous problem with it. So in the previous problem, we had two eigenvalue. sorry, we had two eigenvalues, and we found the eigenvectors for each one of them. When we found the eigenvectors for -2, we realized that every eigenvector is a linear combination of those two linearly independent vectors. So the basis here consists of two vectors. Means the dimension, which is the number of vectors in a basis, is equal to 2. This is called the geometric multiplicity of lambda equal -2. So the geometric multiplicity is the number of vectors in the basis of the eigenspace that correspond to it. For lambda equal 3, the algebraic multiplicity, sorry, the geometric multiplicity is actually only equal to 1. So let me practice a little bit, a simple problem. Here. Suppose I give you the following matrix, and I give this problem on purpose. So forget about that. This is a matrix. And I ask you the following question. Find the characteristic polynomial of this matrix. So look at it carefully. What is the characteristic polynomial? It's the determinant of A minus lambda I, which is equal to what? What's the determinant? Means this following. I have to take a lambda from the terms along the diagonal. 0, 2, minus lambda. 1, minus 2. 0, 0, 2, 3, 0, 0, 0, 2. That's the characteristic polynomial. We have to compute it. I will tell you in a second, Matthew. We have to compute it. Now, I don't know if you guys have seen it, but I'm sure Professor Tarfolaya have told you that when a matrix is a triangular matrix, it's triangular. This one is a triangular. It means everything below the diagonal is a bunch of zeros. What's the determinant of this matrix? You can compute it if you want, but usually when a matrix is triangular, it means everything below the diagonal is 0, or everything above the diagonal is 0, then the determinant is the product of the term along the diagonal. It has to be triangular. It means everything has to be 0. If you forget about this fact, it's not actually hard. You just find the determinant. So if you do expansion across the first column, you will get 1 minus lambda times the determinant of this matrix. Again, first column, 2 minus lambda times the determinant of this matrix. Again, you repeat it yourself. So, sorry, I forgot two things. That's 2 minus lambda and 2 minus lambda. So the determinant is going to be 2 minus lambda, 2 minus lambda, 2 minus lambda. It means the characteristic polynomial is nothing more than another word for the determinant of that. So that's equal to this. Just checking the language. Now, find the eigenvalue and state their algebraic multiplicity as a way to remember what it means. So find the eigenvalues. Eigenvalues, it means you're solving this. If I solve that, I get lambda equal to 1 and lambda equal to 2. So this, the algebraic multiplicity, is 3, because that's how many times this occurs. And this is algebraic multiplicity of 1. Okay. Finally, find the geometric multiplicity of lambda equal to 2. Find the geometric multiplicity. It means we have basically to find a basis for the eigenspace that correspond to lambda equal to 2. And ask ourselves, okay, how many vectors in the basis? So geometric multiplicity is the dimension of E2. That's a geometric multiplicity. So we have to find the eigenspace. Then we have to solve a minus 2ix equal to 0. How do we solve? Okay, the regular. We set up the homogeneous system and we solve. Okay, we solve a minus 2I, so we get this matrix. Solving means you have to go to the echelon form. All right, here I have minus 1, 1, 3. That's already in echelon form. I am in a good shape. I solve. Okay, I have only one free variable in this problem, which is x2. x2 is free. X4 is 0. x3 is 0. x1 is minus x2. So it means that every eigenvector has the form a scalar times minus 1, 1, 0, and 0. So the basis for E2 consists of one vector, means the geometric multiplicity is equal to 1. So that's the geometric multiplicity, is the dimension of E2. Okay. Right, I have definitely to stop at this stage. Please do your homework for next time, because this is not hard, but it's crucial, quite important for you. Okay, please go to your quiz right now.